Welcome to another episode of the Func Prog podcast with me, Christopher. In today's episode, I'm speaking with Aram Hăvărneanu, who is, where should I start? So Aram used to work on operating systems and embedded systems, like real low-level stuff. In the process of trying to improve the status quo in that area, he got interested in programming languages and type theory, and he's also worked on the ARM64 and SPARC64 ports of the Go programming language. He worked on the Q language at Q Labs. We'll get into that a bit later. And right now he's also working on his own programming language. So yeah, today we will be talking about quite a bit about type theory and programming languages, I imagine, and of course functional programming as well. And welcome to the podcast, Aram.
Thanks for having me here. Really,
it's a great pleasure to have you on.
Oh, the pleasure is mine.
You're coming to us from the heat-stricken Austria, right?
Yes, it is. It's people don't realize how hot it gets in the summer here. Especially in these old historical buildings.
Yeah, and it's we as Europeans we don't have the advanced scientific technology like AC.
Oh yeah, very advanced. So yes,
we have to we have to rely on the more conventional methods of cooling down. I don't know, being in the shadow, etc.
Yes.
But also you had quite a dramatic accident a while ago, right?
Yes, I did. I've broken my arm in 4 places, and also hit my head. Also had microfractures in the other arm. So all of this happened while I was on a scooter, on an electric scooter. It was a technical problem. So I would recommend people who ride on those things to either get protective equipment or perhaps not do it at all, because they're very flimsy, and the failure mode is quite you don't fall in a nice way. Let's put it that way. And I was, of course, being a programmer and writing a lot, I couldn't write for quite some time. But recently I've gained most of my functions back, and now I can write and program, and it's all good.
Okay, so you have recovered from
I'm still recovering, but I recovered enough to be able to not have any problem typing. Let's say it that way.
Yeah, I mean those things are pretty scary, and like you said, the failure mode is usually that you're sort of catapulted.
Exactly.
Bars,
Yeah.
I've spoken to multiple people who have had arm fractures.
So,
be careful on those scooters and be safe out there. But anyway, where should we start? I've been following you on Twitter for some time, and I recommend that everyone check out Aram's posts, because you usually post very interesting stuff.
I try to keep the level, the intellectual level, as high as possible for Twitter. I try to raise the bar.
Yeah. I mean, you make good use of the premium feature.
It's great that you can actually write longer posts now with more nuance and. Yeah,
it would be hard to fit all of that into 280 characters. And there was this one post in particular that sort of piqued my curiosity and really sent me down a pretty deep rabbit hole. And that was your post about, and I'm actually looking at it right now. Where you were talking about Curry-style type systems.
Yep.
And Curry-style type systems as opposed to church-style type systems. But maybe we can start with exploring a bit what is the difference? What is a church-style type system, and what is a Curry-style type system, etc.?
Yeah. So I'll give several explanations. Some that just describes how the system is implemented, some more perhaps more philosophical, but Curry style versus church style, or perhaps you can also call them like extrinsic typing versus intrinsic typing.
Okay, yeah.
With the Curry style type system, what you're doing is you have a language which has an operational semantics, which doesn't say anything about types, and which could be, for example, untyped lambda calculus. And then you have an external process which assigns types to terms. Now, this means that terms in your language are essentially untyped or unannotated lambda terms, and all computation is not type directed, because essentially the semantics doesn't know anything about the types. Rather, types are an external judgment. Now, this is one way of doing it, and the reason. First of all, why do we have types anyway? What do you want? Why do you want types anyway?
Many Python programmers are asking the same thing.
Oh yeah. Sure. So from a let's just say software engineering perspective, the reason you want types is because you want to avoid runtime errors. This is the famous quote from Wadler, like well-typed programs can go wrong. So types. So this is one aspect of typing. Of course, it's not the original aspect of typing. The original reason for typing was to avoid mathematical paradoxes with the naive set theory. So essentially, we invented types to impose a syntactic discipline upon the constructions that we do in mathematics, such that we maintain consistency. And the specifics, like the original theory, the way we do type theory, even in mathematics, has changed quite dramatically. Like from the at first it was this thing about just fixing set theory, whereas of course nowadays we're constructing logic from types directly, using derivative of Martin-Löf type theory or something like that. So from a software engineering point of view, it's about avoiding runtime errors, but from a mathematical point of view, it's about mathematical proofs and mathematical reasonings, which of course can be applied to software engineering in the sense that we can reason about programs. But also in a more philosophical sense, what are types? Because you can give definitions like types are this syntactic discipline or whatever, and this is exactly what you do with for example a church style type system. You come up with this. These are the rules that how we can construct and deconstruct types, and this is it. And it's that's a very ontological viewpoint, but there's a more philosophical aspect of it, which essentially I claim that types are meanings, in the sense that types are how we mean, or types are how we think about things. Types are what we have to construct in order to understand something, like to have a mental model of something. If you start with no understanding and you do sort of like a scientific process or like a empirical process, that turns out into the empirical process turns out to be like an inductive thing. You start constructing mathematical models based on induction and so on. And essentially, to understand, you have to construct a model, which in the most extreme sense, it can be a mathematical model, and then it's like perfect. Usually, it's something just in our minds that we don't necessarily have a formal grasp of. But I claim that deriving structure from something means ascribing it a type. And when we communicate, if you don't know anything about a particular thing, and I'm trying to communicate with you and I'm trying to explain the thing, what I'm really communicating is the type. I'm trying to convey to you my notion of a type in such a way that we come to an agreement. And then I claim that all these mental types that we think about and construct, either mental models or scientific models or mathematical models, then get they could get a formal reification, let's call it, in an actual mathematical language where it actually has types. And these sort of formal systems, okay, so as I said before, with query level types, essentially we start with computation first.
Okay.
And then we observe the properties of programs. For example, we might not want, with untyped lambda calculus, there are non-normalizing terms. There are diverging terms. We might not want that. I mean, it's arbitrary.
But like in unbounded recursion, for example.
Exactly. Which, I mean, yeah, that could be a good thing, but we might not want it for some reason, or basically we want to make distinction between terms that's meaningful to us in some sense. And this happened to Church, who invented lambda calculus, and it was proven very quickly. Was proven inconsistent, and then he invented simply type lambda calculus, essentially to fix the problems with lambda calculus. Now, okay, by the way, the way they were doing, we were going to talk about dependent times and stuff like that, which are behaviour quite different to simply type lambda calculus and the Howard isomorphism and stuff like that. This was before any of this, but the point remains. He wanted to classify lambda terms based on some criteria, and it turns out that at the level of simply type lambda calculus, you have this choice. You can either keep untyped lambda calculus and impose this external discipline on it, which is called Hilbert-style, actually, not even if it was on Church lambda calculus, or you can take that terms without a type, terms that are not assigned to a type are meaningless. You can say that types come first, and the only terms that are meaningful are those that are assigned to a type.
Okay.
And you you cannot separate the two. Essentially, all the terms are typed, and this is what happens with Church-style type system, and it's the most common one we use today in most languages. Now, this for simply type lambda calculus, the typing discipline that you can obtain using these two methods is exactly the same. But for more advanced type systems, this is not the case. They can type things in a different way. Some things are typable in one system and not typable in another system.
Yeah, there's a, how can I say? So the in the Church system, like the types come first.
Yeah.
And in the Hilbert-style system, like computation is first, and then you try to sort of like externally you can try to impose restrictions and sort of say like, okay, this program might not terminate, for example.
Yeah.
It's there's a lot to unpack here.
Yeah, and I think there are two aspects of it. Is first of all, it's a technical distinction which might sound like something that's perhaps not so important, in the sense that we have two different ways of doing type systems. Maybe one is better than other in some sense, but it sounds like a minor thing. But to me, it sounds like to me, it's not a minor thing at all. Because when we're doing Church types, that is, when we say that types come first and then computation is assigned to types, Essentially, it is much more difficult to model an open world. It's essentially a closed world of types. So we are working in a closed type universe, which may be desirable, for example, in mathematics. Like most theorem provers use Church types. I mean, the only ones that are not using it is are New Perl and Sedil. And Sedil is very experimental theorem prover, of course. And I mean, New Perl was somewhat popular, I suppose. But Lean and Agda and all these use Church-style types. So yeah, there can be advantages in mathematics and stuff like that. But
yeah,
I'm interested in modeling, let's call them the real world and let's say subsystems of larger systems which operate in a ambiguous context or a context where the environment around the system can change and so on. So to me, it's clear these systems already exist. And they are written in all kinds of languages and stuff like that. And I'm trying to impose a type discipline on the system also for engineering reasons, but also for comprehension reasons. I'm trying to understand these systems. But as I said, the systems already exist. Whatever type system they might already be using. So the type systems that I'm interested in have to be a Curry-style type system, for this simple fact that the computation already exists, and I'm trying to find properties of the computation that already exists. And
okay.
Yeah.
So is this the distinction when you said like there's an open world versus closed world assumption? What does that mean exactly? Like when it comes to type systems, or like just in general? Because I recognize this term from logic as well.
Yeah, that's a good point. Essentially, we in a real world system, in a real world program, the system is designed to operate on a finite amount of information, and it can only take decisions on that information. But it cannot take decisions, or rather it shouldn't. It shouldn't take decisions based on the absence of information. Because as the environment around the system evolves, the properties of the information that's not yet taken into account of can change. So you do not want to commit to giving it any specific meaning or something. Basically, this is one aspect of it.
Because it's like, isn't it the case that like when you have a closed world assumption, is sort of like you have all the information at hand, basically. Like any statement that is not like provable within the system, or any statement that you haven't made, is sort of like automatically false. Whereas in like an open world, it's more like everything is true until proven otherwise, kind of.
You're right. This distinction with the closed versus open world kind of mirrors the distinction between intuitionistic logic and classical logic, in the sense that in intuitionistic logic you're interested with provability. So having a finite amount of information, what does it entail? But we don't say anything about the information that we don't have yet, essentially. Whereas in classical logic, with the law of excluded middle, that's exactly what we're saying. If it's not this, it's the other way around. It's a Boolean, that's a in this distinction, this exact same distinction. Of course, intuitionistic logic and classical logic have models which I mean, it's not quite true that they behave like sets. In fact, I'm probably gonna explain later why they don't behave like sets. But roughly speaking, you can sort of build things which are seem to be set theoretical models, some of these sets have complements and some of them don't, and that basically means if you have closed world assumption or not. And I wanna be sensible to this distinction between refutation of information and absence of information, because it really does come up in real world systems all the time. And actually, this is one of the criticisms the dynamic type people have on static type programming languages. They think they cannot model an open world. Probably this is one of the things when they say that types are too restrictive for them. It's not true. Of course, we can model an open world, but I say that with a Curry-style type system, it's much easier to model in open world, and it's much easier to be flexible about it. In the sense that, for example, in a church-style theory, you always have to create, every time you want a new sort of object, you have to create a new type, and you have to construct a value of that type. Well, when that happens, first of all, there's an ergonomic thing. You have to do it. You have to explicitly do this creation. But second of all, you lose the original. Well, you don't lose it because you can unpack the thing you got, but it's this constant packing and unpacking of things just to keep track of properties, which really gets in the way in a software engineering sense. Whereas with a Curry-style type system, it's much easier to have multiple types for the same term, these multiple types, which represent different properties, do not necessarily interact between themselves, if not necessary, but also with the term itself. So it's much easier to keep it separately, so you do not have to pay the cost of always packing and unpacking things just for them to have like a fancy type.
Okay, yeah. Well, you said a lot of interesting things here. So let's see if we can sort of unpack that. Yeah. So the one thing, and I don't know if this is also related to like open versus closed assumption, but I think something interesting you said was the thing that in Curry-style type systems, terms can have multiple types simultaneously.
Yeah.
And because like in a church-style type system, and again, I guess this might be where the closed world assumption comes in. Once you've decided that a term has a given type, it is that type and that type only, right? Yeah.
Well, I mean, first of all, from a syntactic point of view, even with a church-style theory, if you write some term down, it can absolutely have different types. For example, if I write the identity function down, x arrow x, I can give it the polymorphic type, the one that you expect, so it works for every type. But I can absolutely give the same syntactic expression, just a type int to int, if I choose to do so.
Yeah.
So yeah, I mean, of course, the church and Curry typing disciplines are very closely related, which is why the reason, even in a church-style language like Haskell, we can have type inference. So these things are related, but because first of all, Haskell is a church-style type system, but we don't really write down the types because we have type inference for us, right? So types can be computed from some annotated terms, but the point is, once you made a choice, like if you choose to type the identity function, instead of saying for all a arrow a, you type it as int to int. You made that choice, and you cannot back down from it. You cannot discover that it has a different type by also. So you have to commit to a choice.
Yeah. So I guess this also applies to, for example, type classes. Like, I mean, a type class can be inhibited by or inhabited by several different types, but
Yep.
once you've picked one, like, that's the type you're gonna get.
Well, actually, this brings up a good point about type-directed semantics. So, with Haskell or any language that has type classes or their equivalent, essentially, the semantics of the language depends on the type, in the sense that what will happen depends on specific type, which makes it not a query-style type system, even
it's
though
intrinsic, right?
Yeah, like of course you can compile. Of course, when you compile Haskell, you will compile to some intermediary language where your type classes turn into dictionaries or something like that. When you have dictionary passing, and of course, a language with dictionary passing or with explicit dictionary passing is perfectly compatible with the query-style type system, because the essentially you encode behavior into a value, not a type. Essentially, that's exactly what the purpose of dictionary is. But the point is that the original source language cannot be a query-style language because it is type-directed. Right.
Yeah, and I guess this is also, like, I saw this blog post from Eric Normand, from the, like, giving a Clojure perspective on this, because Clojure has this, like, opt-in type system called Clojure spec.
Yes.
And I think I guess that's a pretty good example of an extrinsic type system.
Absolutely,
or like a query-style type system.
Absolutely. TypeScript as well, because JavaScript already exists, and TypeScript just essentially is a type discipline that's imposed upon JavaScript. But yes, Clojure, yes, and I'm not in the Clojure ecosystem, but as far as I understand, it's precisely this open world flexibility that they want to have, which is why they have their type system extrinsic. Oh, and another advantage, by the way, of of extrinsic type systems is that you can change it.
Yeah, you can have, and you can even have like multiple type systems.
Exactly, you can have multiple ones. But the problem with changing type system is a very serious problem when you're doing a new programming language. For example, my understanding is that when they were designing the Koch theorem prover, now it's called ROC, the ROC theorem prover, they had the calculus of constructions, and I think in the beginning they were interested in only doing lambda encodings. So they didn't want to have native inductive types. They wanted to encode everything into functions. Now, but late 80s technology or understanding of computer science was not enough, so this was feasible, and they couldn't do it, so they had to change to calculus of inductive construction, which has native inductive types. But the point is they had to change the types, and this is quite fatal for a programming language if you have existing users and existing things. Essentially, you can only evolve your language, including its type system, in a compatible way, and a church type system really forces you in a very specific corner, and that's, I think, if this is an avoidable problem, it should be avoided. And another thing, like as I said, types represent properties of terms, and more fancy types represent more subtle properties of terms. And as the language evolves, maybe you want to understand in a formal sense, or in the sense that the compiler can do reasoning about your code, or even proofs or something like that, on more complex encodings that you have in your code, which means fancier types. But you want to be able to evolve this type system in a way that it doesn't invalidate any information that it was known before. So it should be, let's say, monotonic with respect to additional information. You should always be able to add more information to your types and not break any knowledge that you had before.
Mm. Yeah, I guess I had Fernando Boretti on here, and I think I guess the Rust type system is a good example of this, because they sort of keep evolving the borrow checker to be more permissible, so that it will allow more programs, but it still keeps backwards compatibility because all the valid programs are still going to be valid. It's just that like the category of valid programs
and
increases.
We can see this work in Rust. It's exactly right. Rust, in terms of its type system, in the sense of describing shapes of values and stuff like that, is absolutely a church-style type system. But of course, they put borrow checking. Also, they put it in the type system, and that's an external analysis that they do on programs, which they do change over time. That's actually quite a good example of one aspect of their type system is curry based. Yeah.
But like, would you say, like, for example, a static analyzer, for example, would that be an example of a curry style type system?
Yeah, it would be.
Okay.
It will be quite. Usually, static analyzers are relatively ad hoc, or usually they try to fix problems or identify problems in languages which have relatively poorly behaved type systems, such as C, let's say. So they're absolutely. I mean, they do more than just a type system, depending on the specifics. For example, I mean, where is the boundary between a type system and a full program verification? And in my opinion, it has to be with the automation. Like types are for lightweight verification, essentially, with relatively little effort from the programmer.
Okay, so the on the opposite end, you have things like proof assistance.
Oh yeah, yes.
I think, I guess that's one thing that people keep bringing up when against dependent types, is that people don't want to write programs in a proof assistant. But I guess there's a middle ground here somewhere.
Well, I think you're right. So it is true. Most people do not want to write proofs in a proof system. On the other hand, people would like to get some advantages that dependent types give you, even if they don't do full program verification. And this is a very difficult problem, I believe, specifically because they use church-level types. First of all, there hasn't been that much research into this. Idris, of course, is the prominent example which tries to meld practical programming with dependent types. But in general, dependent type languages have been strongly for theorem provers and stuff like that, more so than writing programs. But yeah, so the problem is that dependent types are very viral, sort of, so to speak.
So they spread, sort of.
They do spread, and proofs get very entangled with the programs. And okay, I guess yes, I suppose you could sort of ignore dependent types and just write a simply typed program, but then you don't get any advantage. And then if you want to get some advantage, then you introduce some dependent types. It's a very costly thing that you have to do, and I believe it doesn't have to be the case, because you should be able to view your program as a simply typed program if you choose so. But you should also be able to view it as a dependent type program if you choose so, again, in parallel. And these two views should not interfere with each other necessarily. And one thing that proofs do, I mean, from an engineering point of view, proofs are great because they're universal. Like tests can only test like a finite amount of properties, whereas a proof is a full proof of it works for everything.
Yeah, exactly.
But proofs have to be written with your code at the beginning. Otherwise, if you use dependent types, otherwise it won't even compile.
Yeah.
Which is, I mean, yeah, if you really need full program verification, you're going to pay this cost, but it's very expensive. So what I would like to see instead is people write their programs unburdened by the cost of dependent types or anything like that. They just write programs as normal, using simple type system, write their tests and so on, iterate on their design, come up with something that kind of works or maybe really does work, and then if you are really concerned about correctness, once you get something working, you should be able to prove its correctness after the fact. This is not the case with any system based on a church style type system. And I think that in order for more advanced type concepts and program verification in general to become more mainstream, we have to reduce the cost of verification, or at least alleviate the let's say the day-to-day cost. Maybe the full cost overall, if you really want to do full verification, it's just intrinsically difficult and it's always going to be expensive. But at least you don't want to pay the price day-to-day by losing development velocity, because for everything that you turned out, you have to throw it away anyway for some unrelated reason. First you have to prove it's on correct. So that's, yeah. So I as from a flexibility point of view, I really want to separate proofs from programs. By the way, you can absolutely separate programs from proofs even with the church-style type system. However, then you get into the problem of proof fragility. In the sense, anytime you're gonna change your program, you're gonna destroy the proof most likely. And yeah, I mean, you can keep them separate, but they're still separately syntactically or even semantically. They're in different categories, but they are tightly coupled. So the real thing is to reduce this coupling as much as possible.
Yeah, I think you touched on something important there, which is like you kind of have to meet people where they are.
Yeah,
right?
yeah.
It's and I think the success of TypeScript kind of proves this, because it was JavaScript's type system, or lack thereof, maybe was a known pain point. Like, people had, it was real production problems. I mean, you've probably seen on some websites, like, your order of like undefined has been completed or something like that.
Yep.
So people saw this and it's like, okay, this is a real issue, so let's try to fix it. But then, like, I think the jump from like it feels like now we sort of started dragging people towards using, I don't know, like ML-style type systems, but the leap from going from there to writing proofs in a dependent type language, it feels like it's a bit too far.
Oh, it is. It is.
Yeah, but there was something that you said that that caught my attention, and that's like, when you were talking about this, like packing and unpacking of types.
Yep.
Or did you mean like in the context of, or maybe I should rephrase the question, like, because one thing that's quite really common design pattern in, for example, Haskell or like ML-style languages is that you have a sort of primitive type, like a string or something.
Yep.
And then you want to like sort of show the rest of the program that this is an email address.
Yeah.
Or something like that. And then you have like a new type constructor that's like sort of a smart constructor for this new type. And you kind of use this as an impoverished version of a proof that this is a valid email address. I mean, but then you have the problem, like you said, like, okay, now everywhere in the program I can sort of see that, this is an email address, but then you have to unpack that somewhere. Like, when you want to, for example, as soon as I want to send this to an external system, I need the underlying string. Then I need to sort of like grab that. And I mean, is this was this the problem you were referring to? That's my first question.
Yeah. So one problem with packing and unpacking is that it's not commutative. You pack it, especially if you have several types. Okay, you have a string. Maybe it's a user. Okay, it's or an email address or something. Okay. But then maybe you need another distinction. Is this like a administrator or something? And you have another type that wraps that type, and so you create these types that wrap each other. But then to unpack them, you have first of all you have to pack them in a specific order, and then you have to unpack them in the opposite order. Whereas what you're really interested in is if they have these different properties. If this a real user or just some random string, or is this actually an administrator? And you should be able to reason about these things independently, and you should have commutativity. Let's call it commutativity of properties, right? Yeah. And yeah. By the way, you really see this problem when you're doing like a compiler. Because you keep track of all these properties, like, okay, this is an expression. Okay, but this is an integer expression.
Yeah.
And then you try to do this sort of thing with GADTs, but GADTs never work for this, by the way. Yeah, don't do that. It doesn't work, unfortunately. So, and I actually this is quite a good point, because the sort of language I'm designing right now, it comes from this exact pain point of I have identified two key things that a low-level language has to do in order to do well in this space. How did I identify these two things? I was working. This was when Rust became more stable and like a serious programming language, and of course they tell you that Rust is great for low-level stuff. And yeah, of course, if the alternative is C, it's such a big improvement that it's hard to argue with that statement. But I will argue with it. It's not as good as I want it to be. We can do better. And one of the problems I had was that I was writing memory allocators, and not just virtual memory allocators, but also physical memory allocators, because this was in the kernel, like page allocators and such. And all of this has to
so like very low level stuff.
And I've done a lot of work in this space, and I know how to do it in a very good way. I mean, these things are memory allocators are relatively well studied things. So I had the design exactly how I wanted to do it, and it's not expressible in Rust. And I tried all possible encodings and macros and everything. And my criteria was that, I mean, of course it's possible with unsafe, clearly. That's how I did it. But I don't want that. I want a language that's intrinsically safe, even for this very low level sort of situation. And what we can't do in Rust is two things: doubly linked lists, intrusive doubly linked lists. Now, if you go to, I don't know, some Rust documentation, they're going to tell you, don't do this. No. If you actually write a high-performance memory allocator that's also good for as a physical page allocator, you cannot do it without this feature. It's not possible.
Okay, so it's like a hard requirement.
It's a hard requirement.
Yeah. Right.
So this is one requirement that I wish languages to have. And it's a solvable problem, by the way. Even in Rust, you could solve them if they change some things about their design. But another thing I want to do which appears again and again using when you're doing low-level stuff, including things like parsing packets and stuff. But it's, as you said, you give meaning to terms by essentially when you're parsing, you're doing proof reconstruction. So you give you take some term and you create this algebraic data type which tells you what it is. One problem that a simple algebraic data types have is that they are they're closed. Again, it's the closed versus open thing.
Exactly. You have to show, like, you have to enumerate all the possible constructors.
Yes, you have to enumerate all of them. You cannot abstract over some constructors only. Because, and that you might want to do that because that's exactly part of type refinement. Like, you have this giant constructor which has 100 cases, and as we learn more about it, we learn that some cases are impossible, and then we want to be able to have the same term without unpacking and repacking it in a new type. First of all, for ergonomic reasons, but especially for performance reasons, and also for memory allocation reasons, is that we might not be able to do this repacking of the type because we might not in a linear setting like with Rust, we might not be able to consume the original one because we only borrow it, for example. So it really has to be the same value that's viewed through more and more precise types. Now, in a language like OCaml, which has polymorphic variants, this works. Although they do it, I mean, I would not do it that way, but they did solve this problem, this particular problem. And by the way, again, JDTs do not solve this problem because JDTs support type refinement, but they do not support type expansion. It's again making those committed choices. Like if you refine a JDT, you commit to it. You cannot abstract then over other possible instantiations of the JDT which differ in different indices. Again, with dependent types you can do all of it, but in a simply typed setting, this is quite a different thing. So what I want to be able to do, and which is, I think, the power of query types becomes apparent here, because we have these ways of constructing types specifically through their constructors, and we know all of them. But then we want to be able to quantify over specific constructions which only use some of those constructors. And we want to be able to do this quantification over existing values, because in a language which has linearity, so you have to reuse the same value, the value might be tied into some other data structures and you don't want to get it out, and you might not be able to get it out. And by the way, you see this in Rust again, because how would you solve this problem in Rust? I mean, the context of what I was saying initially with designing a memory allocator, you can't solve it because then you're dealing with properties of existing memory. Essentially, you have untyped memory that you have to, let's call it, imbue with a type and give it to someone else, but you have to reason and operate on the specific piece of memory. But in general, in a higher level setting, when you're not interested in this, you would use something like cell or ref cell or something where you can swap pieces in and out of data structures, basically. But it's to swap something in, you have to put something back. So suddenly, and often you don't have anything to put back, and you just have to encode the idea that there's nothing there. So you're going to put an option type, and then it's always these. Every time you see in Rust ref cell, it's always like RC of ref cell, or maybe it's the other way around, of option. So it's always three types, one after another, which again is the order-dependent wrapping problem that I talked about before. These things should be independent, and ultimately I would rather operate on the larger data structure and do not have to swap anything in and out. That's how I would do these things. Probably, I think I went on a tangent. I forgot the original question, but yeah.
No, but I think there's the interesting thing here, and like what sort of gets backs to the problem. And you mentioned a bunch of solutions to this, like the fact that I think anyone who has worked a bit with like some types know that it can be quite painful because they are closed. As a concrete example, let's say you have an either or a result type, and then you have two of those that are parameterized on different error types. Like even if even if the success type has the same type, you still cannot combine them seamlessly because they have different error types. So you have to sort of like construct a new supertype that you cast them to, and like this is not always a big deal, but it is sort of painful. And like you mentioned, there are solutions for this. Like in Scala 3, for example, there are union types which are leveraged for, I think, this kind of like error handling in SIO, for example. I know they use it to like build up the requirements for the environment. I think there's a previous episode of this podcast where we talk about this, but and then you also mentioned polymorphic variants in OCaml, where you can sort of I sort of forget how that works. You can mix and match constructors from different subtypes, or
so in a polymorphic variant, constructors do not belong to a single type. You don't even have to declare types. You can only use only anonymous types. So you essentially can always create you always have like an infinite amount of constructors to choose from. Just pick a new name, and then you can put type bounds for in functions. You say we only take this particular constructors and so on, and you can specify if you want it to be closed and or open. And by the way, the rock language only has polymorphic variants, so it doesn't have normal variants. So that's interesting. You can do that, and it's useful. Absolutely, it's useful. It's not enough. I mean, it's something. But it's not enough, because this allows you to be very flexible to constructions that essentially use polymorphic variants. But for example, what I would like to see is being more. If you think of, for example, the representation of a subtype, that is, it has a tag and so on and so on, and then there's space for values which has different types depending on the tag. First of all, you can describe this using dependent types, in the sense that you consume the tag and take a decision what's the value, what type is the payload, basically. You have to be able to express this thing in a low-level language, because that's essentially what an RPC packet is, or a network packet is. It can be many things, and it's self-describing in the sense that it has tags and whatever. Like the structure of it is enough to determine the type, but it's a thing you have to do at runtime. Basically there's your dependent type right there. But then if you have this sort of possibility of interpreting things as types based on a value, then you essentially can encode your own polymorphic variants if you want. So you do basically this feature gives you everything you need. So you don't necessarily need something like a polymorphic variant. Which my problem with polymorphic variants is I'm a huge fan of Curry level type systems, as you can imagine, which work very well with structural typing and anonymous types, because you don't have to name types. But that's their problem, because I think in types, and I design program in types, and I write the types first, always, basically. And with polymorphic variants, I mean, you can write the type down, of course, but the assignment, it's just the types in a polymorphic setting, a polymorphic variant setting, are just like aliases or something. They don't matter. But I want to matter, and actually, even though I want to have, for example, when I view an abstract syntax tree and I want to view it as like we're just having expressions, or maybe I want to make a distinction based on their type, or maybe I want to have more information like location information. I mean, I gather this location information when I compile the code, and then it just gets in the way. I don't want to always see it, so I want to be able to forget it in a sense. But it's just a view on the data that's already there. It's not like I'm reconstructing a new type that doesn't have the old information. It's more like an existential type, but even then, I don't want to hide the information necessarily forever. I want to be able to recover it. Anyway, I want to have this relation between some types, and I want to make use of the relation between some types, but I still want to be in control on the specific constructors that are allowed to be used in specific settings. And polymorphic variants are too open. You cannot just say exactly. It gets really, really difficult, or you have to, I guess you can be strict, but you really have to put a lot of types in. So I want you lose like exhaustiveness checking, for example, unless you're strict. But I do want exhaustiveness checking. I just want to be flexible. I just want to be able to see a type through multiple views. But in a specific views, I want to have full information about it, including exhaustiveness checking and all that. So yeah.
So to see if I understood this correctly, I mean, one issue you have with polymorphic variants is that, like, let's say your language only had polymorphic variants. If you say, like, I want to be able to represent an option type, for example, your constructors would be like, either I have some of this thing, or I have none. But with polymorphic variants, you could also like go and mix in other stuff in there, like, so all of a sudden it's like it's some, something, or none, or true or false, or just whatever.
So it's being I think the regular variants are not flexible in the sense that they force you to a specific. If you have a value, they force you to eliminate it in a very specific way that's derived exactly from the constructors, basically the inverse of the constructors, and that's very inconvenient. Basically, but the fact that you know all the constructors is useful information. So you want to be able to reason about the fact that there are no more constructors. It's just these ones. Except in this other setting, you want to be able to make sure use of the information that you know that it's some specific constructor, basically. And yeah, I think that's how I would like to see a type system. And another thing with option types or error types is, I mean, in Clojure, they make a big deal out of it. Is that, for example, if you have a function that takes a value, and then later you decide, actually maybe it has to take an optional value as well. You have to, so in a normal language, in a different language, you would have to change the type to make an option, take an option type, for example, and then you break all your callers. But that's and why would you break? And the Clojure people make a big deal out of it. Why would you break all your callers? Because you made your function more general, and yet the callers now have to do extra work to be able to call your function. Specifically, they have to create the type.
Exactly. Everyone who, like, even if you can prove statically that, like in a classic type system, like, and there's I guess you're thinking of the Rich Hickey video. Maybe not.
Exactly. Maybe exactly.
No, but he made a good case, I think, and like, even if the callers are like, all of the callers are like good, or let's say you're introducing the ability to call something with nil, like even the, like, good citizens, or like, in scare quotes, that actually provide a value, they also have to be refactored, because then all of a sudden you have to put like just or a sum or
Yeah.
whatever. Sum instead of just passing x. Now all of a sudden you have to pass like sum x. And
yes, and the problem comes from the fact that in most languages types are both constraints and requirements. So from every type you derive two polarities. How to construct one is useful for constructing, but for example, when that same type appears in a function as a function type from A to B, that type there is in a different polarity and represents requirements. And you want to be able to express constraints on construction and requirements independently from one another. So you want the type for requirements to be related to the type for the construction, because it has to be related, because otherwise you cannot do a compile time proof how they would fit together. But you want them to be different, or potentially different, specifically in this case with errors and option types and so on. Yes, I think it's one. So languages which use church types they don't try to solve this specific problem with errors. I don't think any language does, but they do solve similar problems when the requirements don't exactly match what you have. They either try to do some sort of implicit coercion, or they introduce either some subtyping, or better yet, something like row polymorphism or something like that. So they want essentially to be able to express more flexibility, and they can do with these mechanisms. And then there are like either implicit coercions put into it, or there's like a meta level judgment with why this type fits into this other type. Nobody does it with simple values and option types though. So I don't, in any of this system, it's not the case that if you have an x, it's the same thing as you have sum of x. I don't think in any system it is, but I think it should be. And especially if you look at representation types, because for example, if you look at Rust, Rust does this thing called niche optimization, where basically they can represent an option type using zero size overhead, because if it's a pointer, because it's a decent language like Rust, where pointers are not nil, you can make use of the information that it's not nil. So then you can encode the missing value as zero essentially, and do not impose any sort of extra overhead. Now, but this is just special case thing they do in Rust. No, you should be able to reason about the structure of a value, including things like can it be nil or not nil, or fields. Maybe you want to be able to express things like, this relation between these fields, or there isn't. And one good example of that is if you have, for example, a record type or like a structure. Very often the elements in the structure have to have some sort of relation between them, and in a dependently typed language, you can actually encode the relation explicit as a proof. That's quite it's quite annoying from an ergonomic point of view, but you can do it.
Okay, so just to give a concrete example, could this be for example, if let's say I have a user record, and there's some kind of bool thing that says whether I'm an admin or a regular user. If I'm an admin, maybe I need to have a non-empty list of all, my what would you call it, all of my privileges or something like that.
Right. Yeah. Or a simpler you can that's what I was thinking. That's one thing I'm thinking of. Another thing is you have a user, and it can either be an adult or a child, and it's adult and child both have names, both have an age, but for adult you want to encode the additional property that it's greater than 18 or something. and the child that it's less than or equal to 18, or what I forgot. I'm not sure how what age do people get are adults these days, but
yeah, depends on what you want to do, I guess.
I
if
suppose,
it's like buy alcohol, vote, etc., military service, it's like not everyone agrees.
Yes, but this sort of information is useful to put in a type, in the sense that as a requirement you want to impose this restriction, for example, for some reason, but it's from the perspective of someone who produces the data or the data in the database or something like that. It's incredibly annoying to be able to prove these things just to create the data. So you don't want to do that. You want data. You want producing the data to be as simply typed as possible. Rather, you want to have the extra constraints of what properties the data has to fulfill in order to use it at the call site. So the type for the requirement can and should be stricter than the type for the producer. But it's, of course, that means we can only call it once we have established that property is true, of course, and that we do by checking the age or whatever. And then after we check the age, we gain a compile time proof that it fulfills that property. But notice that this compile time proof is not a wrapper of anything. It's the same data that we had before, just embellished with this extra property that can be independently reasoned about. And yeah, we tell people parse don't validate, and it's great idea. But at some point you're gonna parse enough and decide, oh, this is the type that I want, and it's a parsed type, and okay. But then what you do with the type, it's always the case that you will want to have, almost always the case that you will want to have extra properties assigned to those values, or you only want to reason about subset of them or something like that. And you have to be able to express this property without breaking the producers of the original type.
Okay, I think that's really interesting, because that's sort of like it feels like it circles a bunch of the things that we talked about just now, both with the option case and with this. Because what came to mind when you talked about that, like making things more complex or like not putting the burden on the producer is, I mean, if you look at dependent types, for example, like you can do some very I'm not a dependent type expert, by the way, so take this with a grain of salt, but I mean, you can do a lot of cool things, like encoding fixed size lists, for example, like the classic vector example, and you go like, wow, that's really cool, but the downside is that this is sort of built on like encoding natural numbers in like a piano notation. And like, I guess this is sort of where the literal burden of proof comes in. Like, the producer has to, if I want to say that, okay, I want to get an index or the element at this point in the list, I have to somehow produce like a piano number. And I guess the languages can sort of help you with this, but again, it's sort of like the whole thing sort of hinges on the fact that you're sort of constructing lists and piano numbers in parallel, and I don't know. I think I guess that's a good analogy for. I actually think that, first of all, so if you construct natural numbers in type theory, the reason you construct the numbers in a particular way is because you're interested in induction. Because especially if you do computer proofs, I mean, you have to have induction. And if you do computer proofs, induction is everything. And of course, your natural numbers have to have an induction principle. The problem with that
I mean, that's great. If all you're doing is theorem proving, that's what you should be doing. One thing that we have, that the thing, induction is quite a burden to prove all the time, as you said. And you can cheat a little bit with computation, because at runtime you have usually, for example, like dependent type people, like the example of like a vector append that preserves the length of the first vector plus the second vector is preserved. That's an interesting example, but I think you can do that sort of thing without induction, because you have because you can compute with arithmetic. Yeah, there's a tension between arithmetic sort of operations and stuff like that, and dependently type proofs. There's quite a tension, and it's difficult to do it is difficult to make good use of arithmetic in these sort of dependent proofs, because more or less you lose induction. But I came to the conclusion that losing induction for practical programming in specific cases, because it's a bounded loss, it's not such a big deal. It's way better to have dependent types without induction, without general induction. You can still have particular induction principles, but in general you can still have dependent types without induction, and it's way useful than not having dependent types at all. I would say that. Yeah, I think that's how I would say it.
But in your example, for example, if you like the case where an adult and a child, for example, how would you and let's say you have a function that requires that only I don't know, a buy alcohol function that requires the user to be over 21 years old.
Yeah.
Like how could you go about verifying that this actually works in like and like compile time, and not I mean, the obvious way is to like just throw an exception, like, oh, you tried to do this, it didn't work, sorry.
So I would make a very principled use of flow typing. Like what happens with flow typing, for example, TypeScript has flow typing. That means that in if expressions and conditional expressions, essentially, you gain additional information. Like if you check, if this string is not hello, or if this string is hello, you know that information, and you can put it inside the clause of the if, the body of the if. You do have this additional information, or it could be something like. I mean, the easiest example is with not nil. If something is not nil, I have this value. It may or may not be nil. I checked it. Now I know that it's not nil. It means that in the body of the if, I can treat that as if it is a not nil. Now, the problem with flow typing, and specifically what happens in TypeScript, is that it doesn't go very well. because the compiler has to guess from any sort of arbitrary code that you write, which includes calling functions and stuff. It has to guess what do you really mean by this, or when you try to call, it might refine the type in some sense, but then you call a function which expects one of these refined types, and it will not be able to prove that it is the same type, even if it is, because it's very limited in doing this sort of inferences, because it's very an ad hoc procedure that TypeScript does. So it's interesting that it does it at all, and I suppose it has to do something, because it's critical for ergonomics, because, as I said, we do not want this packing and unpacking of stuff. So it does something, but it's not principled. It's just the guesswork, heuristics, how it does it. But you can be principled. And how can you be principled? Now, first of all, I don't know if we did we mention verse on this podcast before. I don't know.
No,
not yet. Right. So maybe we should talk about verse at some point a little bit. But first of all, verse, the type system of verse is not publicly documented yet. So I'm just guessing here. But this is what I would do anyway, because this is the same thing I would do in Q. You want to be able to give a name type for a property, including this, for example, that it's not nil, or that it's specific to equal to a value, or that it's greater than 21 or something. You want to have this type in your context as a known type. But then in your if expressions and so on, you do not just check if value is greater than 21. You do have to make explicit use of the type to gain information that's salient to the type. So you have to try to you have to try to assign to that type inside the if expression. So you're saying you're saying if v colon this type or whatever. That's a hypothetical type assignment. It's an attempt of type assignment, but it's then in the if branch you actually have the exact information that's relevant to when you try to use it later when someone requires that you pass in someone with age greater than 21, because it refers to the exact same type. So you do have to actually construct, in some sense you do have to construct all these types explicitly, which is exactly what you do with a normal dependently typed language, except you don't create new values. You can just refine the existing ones, and you don't have to wrap anything, but you have to attempt the creation just as well. But you're attempting the creation using normal programming things like conditionals and stuff like that. So you gain additional type information through conditionals by not like in TypeScript by guessing, but by specifically referring to types. And what are types? Well, in verse, I mean, it appears to be that in verse types are partial identity functions, and this is why it works, because you just pass in a value and you get the same value back, except with a more refined type. Now it can fail, but failure is fine, because again in a conditional you always check the else branch or something, or maybe your function, it's the function the function you're in is itself marked as failable. So it's an effect system that's explicit, so you can't forget to do the right thing or something. But the point is that you have to construct these types explicitly rather than implicitly as in TypeScript. It just has to be very convenient. Just use them in if expressions and so on. And by doing that, type values get additional information. And this additional information, it is an intersection type, by the way. It's all the previous information plus the new information independently, and you can make use of all this information.
Oh, very cool. Okay, I have like 3 questions.
Yeah.
At least. So I think first of all, I guess the interesting part here is that like this would be like super awkward to do in like a regular with some types, because I've seen systems actually where you sort of take this approach to the extreme, that you let's say that an input takes a string that's like maximum 255 characters or something like that.
Yeah.
And then you create a new type that wraps a string and that has a constructor that checks that the string is like between 0 and 255 characters.
Yeah.
And I mean, that's very awkward, because now again you have that packing and unpacking problem that we talked about before.
Yeah.
But you're saying, like, for example, in verse, you would still have to create a type that says like this string is maximum 255 characters.
Yep.
But you could like you don't have to like wrap the type. It's both a regular string and it's also a string that's a maximum 255
That's
characters.
that's right, and it's yeah, and also it involves not only that you don't have to do any wrapping and unwrapping, but it doesn't involve any representation change, because the more precise type is a subset of the original one in terms of its representation. So you cannot it just you can keep the representation. Yeah. What really happens, actually, I think this is another way of explaining it, especially in the church versus curry type setting, is that, I mean, in both settings types are proofs by Curry-Howard, but in a curry setting, it's as if, okay, we have this program and we're trying to reason about the program. And then we come up with these types which represent properties that we're interested in, and we can see whether the program satisfies those things or not, or if it does, or if we're not sure, then we can very easily change the program to take that into account and essentially conform to our view of it, essentially. So we take like as an object of nature and try to analyze it and see what properties it has, and see how we can combine programs together and so on. And we do that by essentially doing reasoning over the program, in a sense. But the program is already there, or at least certainly the data in the program is already there. So this question of unpacking versus repacking is not even, we never think about this thing. We just think about data and functions. And data and functions could have different relations between them. There can be internal properties of the data itself, internal relations between different parts of the data, and so on. And we can observe those things. So with the curry type system, we try to prove we try to prove things about systems which already exist and are structured in a particular way. But we don't want to impose any structure. Like we just want to reason about the existing structure, so to speak. Whereas in a church setting, again, types are proofs nonetheless, but and even proofs are explicit in both systems, by the way. It's just that because these things are very, very separate in a curry setting, it's very easy to be flexible and reason about existing programs, whereas the other one, types are more entangled in the program and you cannot really get rid of them. Although in principle a system with church types can have type erasure, although not always, as explained with Haskell, but it could have type erasure. But that's not the point. It's how we think about different things. Or let me even step back maybe a little bit more. We talk about in general when we try to explain the relation between logic and computation to people. We talk about the Curry-Howard isomorphism and stuff like that. Well, that's a meta level statement. Okay, it's because if you look at how people actually use, like mathematicians, how they use lean or whatever, they don't think of Curry-Howard or anything. They can see if you take a dependent type theory such as lean, which is church style, it embodies logic, essentially. You can find logic in it. You can find all the logic, introduction, elimination rules in the language. So it embeds a logic. So it's a quite different thing. It's quite different thing that saying we have computation and somehow we have programs and somehow they correspond to proofs. No, in lean, the logic is embedded in the programming language. It's there directly, and it's such a strong embedding, which is why you can absolutely explain lean to mathematicians without having to mention Curry-Howard or anything like that. You just say, oh, this is how it works, and they see the logic rules that they know intuitively, because mathematicians don't actually know formal logic, but they have an idea of how logic rules work, and they can see them happening inside Lean, so it's easy for them to accept. And they don't think anything about like constructivism, whether the programs, whether the proofs correspond to programs or anything like that. No, they don't have to think about that. Whereas with a church-style system, a church-style type theory, you have types and you have terms, and the terms realize the types. The terms acted as realizers for the types. And it's quite a different thing. It's that first from how you approach the thing, you always think about types, because again you're interested in like doing proofs or whatever, so you always think about types. But then once you think about types and you try to prove something, you can observe that this independent computational object behaves in a way that produces exactly the properties that I want from my type. So there's a very direct and explicit link between the computation and the type. So I would claim that the idea of Curry-Howard is much more explicit in a Curry-style setting, especially if you accept that. I mean, you have to accept that propositions are typed no matter what. But if you accept that, then in the theory of your programming system or programming language, it's an internal. In the meta theory of your programming language, the type judgment is an internal property, which is quite different from a church-style setting where it involves different level of meta logic. So yeah, but in terms of practical programming, it's the idea that we use types to design programs, modules in software. I mean, modules also have types. Like it's a software engineer. It's an engineering thing, and we make use of types for design purposes, also for verification purposes, if you want to have like maximum assurance or whatever. And then and essentially this gives us the language of types gives us a language of design. Like we want to be able to talk about specifications before we talk about programs, for example. But want to talk about specification in a very strong sense.
Yeah, like you want to be able to, I don't know, draw up a blueprint before you start construction.
Right. And then, because types and programs are separate in a fundamental way, we can then try to see if our programs actually match our specifications, or we see where they don't match, and how we can. And ideally, if we find a type mismatch, it should be like a local operation, like an error should come with some sort of, the solution for every error should be somehow localized in the program, in order to be like scalable from a software engineering point of view, to be able to produce it quickly and stuff like that. It shouldn't be like a global thing. This is clearly not the case with the church-style system. It's clearly a global thing. By the way, type inference, if you like typing, one of the reasons why I don't particularly like type inference the way it is done in language like Haskell and so on is it's a global analysis, and all sources of type informations are given equal treatment. Like, the error is never that I'm misusing this value because it's not of the correct type. No, the error is always like there's some inconsistency.
Yeah. And there's no like it's like oh, is it how can I say, is it your like definition that's wrong, or is it the usage that's wrong? Exactly. So you can never tell.
Yeah, and so as far as I'm concerned, this wrapping versus this wrapping behavior that's very much associated with church-style type systems is in some sense you want the implementation, the specification to be separate, like just from good engineering best practices sort of situation. But having to appeal to types which are a specification to wrap them around, you're tying these things together in a way that's not indicative of good software engineering practice, and it's not scalable. And that's why we know, like, we understand that a type programming language, even a simply typed one like Haskell or most functional languages, we understand that they're very effective in preventing bugs if you use the type system correctly. And then the non-functional programmers, or especially the dynamically typed people, are going to tell us, oh, but the cost of types is too much because, yeah, and they're right. Right. The cost has to be reduced as much as possible. And by keeping the specification and implementation separate, which is exactly what Curry-style type systems do, you will allow to reduce this friction, I would say.
I think that the thing that seems most appealing to me, and the thing that with Curry-style type systems seem to be able to do better than church-style, is that thing you just mentioned, where a type can be several things simultaneously. Because I mean, we mentioned Scala, we mentioned TypeScript, and if you see that, like, you know, they can handle union types just fine. Like, and the same thing with polymorphic variants, like saying that, like, this type can be any of these, or like this term can be any of these types. That's not really a problem. But the thorny part, and where all this wrapping comes in, is that when you try to say, like, this type can be all of these types, or sorry, this term can be all of these types at the same time. Like if we go back to the email example, like, you can say, like, you know, this is a string. I mean, that's one way to look at it. And you can also say that I have previously verified that this is a valid email address. And then a third interpretation could be like, this is a primary key in a database. Somewhere. So it's like different interpretations of the same term.
Exactly.
But they're all valid at the same time.
That's a very good way of putting it, and that's exactly right. That types are interpretations for terms.
And there was one more thing I wanted to ask about, like, you know, that verse thing sounds really, really cool, and I hadn't heard about that before. But one thing that I'm wondering is, like, okay, so let's say you have this thing, you say that like the age term for a user is like over 18 or over 20, or even better, like, let's say that you can only buy drinks when you're 21 at a bar, but you're like, you can vote when you're 18. Is there some kind of, like, can you encode this in some kind of, or does it automatically imply that if it's over 21, it's also over 18, or is that? That's a good question. Well, it's a good question. So I think that from an ergonomics point of view, it should imply that. Otherwise, it would be very difficult to program it with the system. By the way, Q does that. So first of all, I don't know. As I said, its type system, I don't think it's been described properly, and I don't know exactly how it works. I would guess it works like this. I don't know. But in terms of Q, for example, yes. If it's greater than, if it's less than 18, you should be able to infer that it's less than 21. There are, this arithmetic inequality, doing arithmetic inequalities and doing proof about inequalities in an automated way is both like, you want to get good errors, you want to get good performance from your type checker. You don't want to just like, oh, it takes too long, or just it explodes and stuff like that, which is a real problem, because systems based on refinement typing, such as
F star and systems like that, which basically, essentially, they allow users to write this sort of refined types the same as we just discussed. Like there's a base type, and it's just a refinement of it. Like we attach additional predicates that we want to hold, and the systems that use refinement types try to prove those things, and you can write inequalities in what we just said, and they try to solve those things automatically using an SMT prover, and it works well when it works well, and it explodes when it doesn't work well, and how long it takes to type check is it's not predictable, unfortunately. So it's quite an open problem how to solve this problem well. One way of solving this, so I don't know the exact solution to how you do this sort of automatic inferences across inequalities and this thing, because I don't know what's the best design. In the case of Q, it doesn't matter too much, because Q is more concerned with. I guess we should talk about Q, because I don't
yes. Let's dive a bit into Q.
All right.
It's been an hour plus. I haven't touched on that yet.
Q is a language that I used to work for Q Labs, which develops Q. I don't work there anymore, but so Q is a language. It's several things in one, and I would say the things. Then maybe we're going to talk about them individually, because they're very. It's many things for many different people. So first of all, it's a language which has computational behavior, and I don't know exactly how to explain this, because it's a domain specific language, but it's an interesting language in the sense, and it's for describing data mostly. It's for describing data.
Like a config file, for example, or
yes, but I think that they're selling it very short. Yes, it is. We call it. I say we. I'm not involved anymore, but I might say we out of inertia, I guess. It's configuration language because it's designed to deal with problems that arise with configuration, and we should talk what that means specifically. Because when people think about configurations, most people who have not worked for big companies like Google or other hyperscalers or something like that, they think of like, my Vim config or whatever, it's like a static file. Who cares? I can be whatever. No, it's not about that at all. So we have to define what configuration means. But anyway, it's about describing data, but it's about describing data in a computational way. So it's not just like JSON, which is a static piece of data. No, it's a language which exhibits full computational behavior. It's a total language, so it terminates. It has a termination checker, but just like with any other total language, the termination checker is an additional piece of technology. So if you remove the termination checker from Q, it's Turing complete. Okay, but it has computational behavior, but it doesn't use the way this is done in most languages is with functions and application of functions. So this is how you compose your program using functions. And then you apply those functions, and computations comes from like beta reduction of lambda calculus, something like that. That's not the case in Q at all. So it's not a lambda calculus derivative in that sense. It works by completely different principles. It works by unification. So it's a logic language, kind of like a data log and prolog. So on one hand, okay, it's a language, it's a logic language, but it's also a type system. People, when I was talking about Q to academic conferences and stuff like that, and of course it's very easy to contrast it with dependent types because it has this rich computational structure and it can compute types and so on. The question ask is like, isn't this just dependent types, or isn't this just refinement types? And I always used to have this cop-out answer, well, no, because we're using set theory, we're not using type theory. But that's not quite right an answer. And actually, it's more subtle than that. And I would say I would say it actually is a type theory. What's the difference between a type theory and just a language which a type system? Without giving just an answer like, oh, it's dependent types or something like that. No, because even simple types have an equivalent, for example, like Curry-Howard, some logic or something. No, I think the difference, what constitutes a type theory is whether it's consistent or not. Like if you have dependent types, but you imply type in type and you make it inconsistent, and it's like in a real practical programming language, it's not a type theory anymore. Although it does use dependent types. So similarly, you can have a simple type thing that is consistent. Such as simply type lambda calculus. And Q is consistent. So it is a type theory, but it is a very weak type theory, in a way that I will explain in a moment. So you can't prove much in Q, but what little you can prove, it is consistent. So it's a type theory, but a type theory for what? And it's a Curry-style type system. Okay, but the Curry-style type system for what? Well, for everything. So for programs in other languages, for data exchange mostly between systems, existing systems in other languages, especially in the context of cloud and RPC and microservices and Kubernetes and those things. You have these different systems which communicate with each other. They exchange data with each other, and we're in this weird world where, like, the industry has finally learned about the benefits of static typing, kind of, and they use more advanced languages in developing their microservices with better type systems and such, perhaps. But at the level of if you step out and view it from afar, the cloud itself, the system itself, becomes untyped because there's no compatibility between how the systems communicate. There's always protocols that are implicit in the sense that you have to think things like first you have to get a token to be able to do some operation that requires privilege or something, and you have to acquire the token before you do the operation. This is basically like session types or something like that. It's not being done because the way that the overall system, like the individual parts, might be formally specified in the sense that it's a real programming language. The system as a whole is more implicit than anything, or it might be declared in some declarative language, but it's not. The declarative language doesn't have any good properties that we expect from programming language, such as being typed, for example, or having like a good semantics, good denotational semantics, being able to reason about things. No, it's just okay. It's declarative in the sense of it's a list of information, but no. Q is designed to type those things that already exist, and usually they're specified in giant million line YAML things or something. But it's also, there's another aspect of it which is more subtle, and which is, as I said, there's RPC between services, and we usually think of they communicate data. That's not quite right, because there's always some sort of implicit DSL going on. In some sense, we have to encode everything we want inside some piece of data, but what we're really doing is trying to make the system do computational effects for us, and we always usually try to add extra semantics to the thing that we're saying, in the sense that we're kind of really expecting to react to what we're saying as if we're trying to send a program and the system runs the program for us, in a sense. So at large scale, there's always this sort of implicit domain-specific languages that people don't even think that they're language, but they are there in the sense that they're rich computational structures that just happen, and they're very difficult to reason about, particularly because they're implicit and they don't have good semantics. But they already exist and they're specified in some other language or whatever. And Q is an attempt to bring order to this, in the sense that, as we just discussed about Curry-style type systems, they can type already existing computation systems, and in particular it's designed to add types to these sort of things. So you can either add a type system to your cloud and get benefits of type systems, such as when you do a modification, you get type errors before you try to deploy them. This is one clear use case. Another use case is to be able to use Q to understand your system, because it's designed in such a way that things from other languages, or especially data from other languages, can be interpreted in Q. So if you think in terms of like denotational semantics of you have all these languages which can be explicit or implicit, as we discussed, that just exist in the cloud or are part of your organization or whatever, and they can be multiple languages and multiple systems. To understand things, we want to understand their semantics, so we want to understand their denotational semantics. So we need a good tool that would suffice, that would work as a denotational domain for these things, and Q is one of those things. So it's a type system, it's a language, it's a denotational domain that's rich enough to do all these things. It's a logic language. It's what else is it? It's something close to it uses set-theoretic types, including union and intersection types. It should be understood in terms of its set-theoretic model. This is not necessarily true for most languages, which you understand. We don't have to think about their models necessarily. Only like people who do like semantic analysis or something have to think about models. But no, Q is specifically designed that you only think about the model rather than the language, to the point where the model is really what matters. As I said, it's kind of like a logic language, and it's designed for flexibility, assigning multiple types to the same thing, but also not only it's design. It has this monotonic property, in the sense that you have a Q program, and you can always add more information to it. So it's concatenative in that sense. You can always add more information to the program, and when you add more information to the program, you only refine it. Now we have to talk about what can we express in Q? Well, we express things. First of all, we express we express properties about, because everything can be translated to a tree, like especially languages that used in industry and such. Especially when you do an RPC, you have to convert whatever it is to data, and it's some sort of tree or something.
So just so I to give an example, if I have a bunch of services, for example, in my cloud, and let's say I have a service A, and then it's called by service B and C, I can sort of outline the I don't know, if I have a REST API interface, I can sort of describe the REST API interface in Q, and then I can also describe how it's used by B and C. And if I change something in like the definition of service A, I also notice how that might break the other services. Is that a valid use case?
It is a very valid use case with the following caveats. So as we said, Q is designed to act as a denotational domain from other languages, because you probably have some infrastructure written in some languages, and this includes things that express data such as JSON and YAML. You can interpret them in Q, but you can also interpret things which have types such as JSON schema and OpenAPI and essentially typed systems. You can interpret them in Q, and you can do the converse operation as well. Once you have some Q computation and you reason about it and you compute in this Q domain, you can convert it back into this other type representation from other languages. And also, not just these like JSON schema and stuff, but also in principle directly with the type definition in your favorite language. Now in practice, I think only Go is supported, and I'm not sure exactly what's the full set of support languages at the moment, but in principle, all the languages can be supported. So yes, the idea, and it's bidirectional in the sense that you can choose the source of truth to be either whatever you have right now, and you just interpret whatever you have now in Q, and use that for checking consistency computationally, or you can take Q as the source of truth and generate those other things. So it doesn't come with any prescription of how you should be using it. It can be used in any way you want. It can be the source of truth. It doesn't have to be the source of truth. It's designed for full interoperability within all these languages, at least in principle. In practice, only some languages are supported, but in principle, all the languages are supported.
So if I have a bunch of OpenAPI specs, I can either feed those into Q and check if all the interactions are consistent, or vice versa. I can describe my services as a Q program, and then the Q can export OpenAPI specs.
Yes. That's true. Yes. Let me just check if we have export for Open. We have import for OpenAPI, but let me see if we have export. I'm not sure. But yes. Basically, that's how you are supposed to be using it, especially since the ecosystem right now it is. A lot of services and systems are described either in terms of OpenAPI or in terms of JSON schema. And the idea is not to replace any of these things. They're just existing things, so we just have to live with them. Rather, we have to be able to interpret these things soundly in Q, and be able to reason about them in the terms of computing types and computing new properties of them and things like that. But then again, being able to use the result back into your existing infrastructure. So it's that thing. So you can. So it has a tree-like structure. It can express all these types that we discussed. Then it can express more interesting types like intersection types. The exact same example that you gave with the email address. Email, first of all, it is a string. Then again, it could be an email address based on some specific way of validating email addresses. Also, yes. So you can have this. However, you can be as precise as you want in terms of intersections about the types, about values. But by the way, it is types are first class in Q. There's another idea about is it dependently typed? Well, it's quite hard to answer, because from a logic point of view, it corresponds to a logic of potentially refutable assertions. So normally in a programming language, in a regular, especially if you're trying to prove anything, you're starting with positive information. I mean, that's the whole point of constructivism. You construct things, and at the end, if you can construct things, if you can construct a value of a specific type that can serve as a proof, and it's very general. You get full logic from this. In Q, it's much weaker, because programs are first of all, what does it mean to run the program first? Because it's unusual, because you can always extend the program after you ran it, but even before. So this is not the case with other programs. Other programs, like in Lambda calculus or whatever, you write your program, and then your program does your beta reduction, and it basically normalizes to a normal form, and then you're done. Nothing else you can do with it. it
returns value, spits out something to standard out, or something like that.
So what happens in Q is that you can write your program. I mean, I call it a program. I don't know if other people call it Q. What is a program? But okay, I call it a program.
Let's call it a program.
It's really a co-program, but okay, it's a program. It represents some information, and it does do normalization. So when you run eval, it will normalize the program to a normal form. Now there are some subtleties here with normal forms in Q. What is a normal form? Because in lambda calculus, you can I can show you an expression, and there's an algorithm. You can determine, is this a normal form or not. Well, in Q, you can't really say if something is a normal form because it's context dependent. Because so you run your program, and essentially what happens, the program partially evaluates. And how much does it evaluate? It evaluates as much as you can, so to speak. But it reaches a point where it's not really in a normal form. It's in a partially evaluated form, but it's in a partially evaluated form which maintains its semantic soundness. So we can talk about this new state of the program. It's not something new, something. It's something that you could have written yourself. So it acts like a normal form in that sense, but it's always refinable some more, in the sense that you can always add additional information to the program and reduce it some more. So and you can keep doing this. You can keep refining the program. When does it really stop? Well, it stops in some sense when it reaches this, when it evaluates as much as it can, but it's not really stopping it because you can continue it. When does it truly stop, in a sense that it's final? When it detects an error, or basically an inconsistency or a type error, or you're trying to prove something that now it's provably inconsistent. So essentially what happens is that in Q you just declare axioms, essentially. So there, almost every statement in Q is treated as an not quite. There are, for example, if you declare data, if you say that x colon 3, well, you really know it's 3, and you really know it's a type. You really, first of all, 3 is both a type. I mean, it's a type that contains only 3 as a value, right? But in general, when you say x colon t in Q, it means that there exists an x. Well, it means several things. First of all, it means that if you're looking for values, it really means that there exists an x, which is an element of t, which is a reasonable thing to assume it means. But it also means something else. It means that x is at most t, but it could be a subset of t, and it's refinable to any of its subsets.
And sorry, what is t in this case?
So if I say x colon int is the set of all integers. It's fully, there's no like limits for size or whatever. But then I can say, okay, I know this information, and it's an axiom. But then I can say x is greater than 0. Okay, greater or equal than 0, and then I know that it's actually only referring to the natural numbers. So we refine the original thing, and then I can say something like x is prime even. I mean, you could potentially define, potentially you can encode primality in Q, I think. Although it's probably very complicated because it's not designed for that. But in principle,
somehow,
yeah, you could certainly you can do much simpler things, like you say x is even or something like that. So what we see is that, and the way it works is it accepts. So first of all, it had the declaration that x is an int. Okay, accepted it as an axiom basically. This is a difference between dependent types theories and what we do in Q, because in Q we only have axioms. It's more like an axiomatic system than something else. So we take it as an axiom, then we say x is greater than 0. That's great, because this new piece of information is compatible with what we knew before, so we accept it. Although we still don't know what x is. So there's still this lingering, there exists an x, which is a value. We don't know what it is, and it's okay. We don't have to know, because we're only doing type level stuff now. But then we say x is even. Again, this is compatible with we just said before, so that's fine. But then if we also say, we add another axiom says x is less than 0, well, suddenly we have a problem. It cannot be both greater than less than 0, and the system will stop, because this is an incompatible system that we have now. And if we were to continue, I mean, you could prove anything, because essentially we have a incompatible information, we can prove false. And so essentially, when we detect a refutation of what? What we said when we said x colon whatever, what we really meant is there exists an x with these properties. But once we say that x is both greater and less than 0, we know that there cannot be such an x. So x is an empty type. And we do not want empty types because we can then it becomes inconsistent. So that's why I say it actually is a type theory, because it cares deeply about consistency. So it will never prove any inconsistent stuff. It can only do consistent things. But it's a very weak logic, because it's only a logic of weak refutations, because it's mostly concerned with this negative sort of information. Like we have to make sure that the thing fits into our model. But we don't know what the thing is, so we're not really saying properties about the thing, and we're not really constructing the thing. This is quite different. When we're saying,
I think that's one of the I looked into Q briefly before this, and I think that's one of the things that's fascinated me the most. Like you said, in a regular, I don't know, programming language, you usually expect the program to, terminate once it's done. But in Q, it's sort of like you sort of when it doesn't have any more instructions, it basically outputs everything where it was now. Like
exactly.
Okay, so this is what you said, and I think another thing that's quite fascinating was that you can like you said, all these things can be out of order as well. Like you can say okay, I mean, you can say that user, this is an I don't know, this is an email address, and they say it's also a string, and that's that matches what you said before, because it should be a string. But then if you say it's an empty string, then all of a sudden it stops, because it can't both be a valid email address and an empty string.
Yes.
And basically all of these things, they can come in any order, which is also quite quite interesting.
And the order independence is a fundamental property. So it's a commutative language, and this is important for software engineering purposes. So, for example, you always have to be able to take a program and refine it further. You don't want it. Maybe what you get is like a module for someone else, so you can't edit the source code. No, but you should be able to refine it out of spatially. It's spatially disjoint, but essentially in Q you can refer to the same value in different places. So it's sort of like an action at a distance sort of thing, which for functional programmers probably sounds alarming, but it's not, because of an additional property that Q has, which is monotonicity. So one of the problems with mutable global data is that, if data changes underfoot, you cannot reason about data. It's always going to be different. So how it's very difficult to design reliable programs using mutable data, especially global data in that sense. Not the problem in Q, because it's true that data can be refined underfoot, but it can be refined only in a monotonically increasing way, which means that whatever information you had about the data before cannot be invalidated. So that's fixed. You can only gain more information about it, but all the previous information that you got about it, it's still valid, so you can still make use of it. And this monotonicity property is absolutely essential. It's absolutely this where most properties of Q come from. And this is why it's possible to write programs out of order and be easy to understand and so on, because it's about how do we understand the program. It's about how much we choose to look. If we want to interested in a value, we can see all the sources of information that flow into it. But even if we choose to only look locally or only on some pieces of information, maybe that's enough to determine whatever it is that we're interested in. And we don't have to look at the other ones if they're not relevant, because any information that we see is irrefutable. So it's absolutely, you can rely on it. And yes, you're right. So you run your program, and look, it's another difference in for example, in lambda calculus. If you try to interpret lambda calculus using domain theory, and you interpret one thing is that you have diverging computations, and you interpret them as say a bottom element or something like that. Well, that's very different in Q. In Q, there's also a bottom element. But the bottom element is basically just we just denote the empty set as the bottom element. So it's a set with no element. It's the empty set, empty type, if you want. Okay, but that's different, because in a normal program, as long as you don't get any errors, you will never get bottom. In fact, you will only get bottom if it terminates. So it's exactly the opposite as with lambda calculus. With lambda calculus, we represent diverging computations through bottom. But in Q, because it's this duality between programs and co-programs, there's this polarity reversal, which essentially tells us that no, only terminating computations can be interpreted as bottom or as the empty set, and there's only one way to terminate a program, and that is to try to construct the empty set, and we don't let you do that because it violates mathematical consistency.
Yeah, I see. So, I mean, what is a co-program exactly?
Yeah, I probably am not able to explain this properly, because I don't know enough category theory to explain it properly, but I can explain this. A data type such as like a sum type is a data type, because it's described in terms of its constructors. So we tell you what the constructors are, which we know that they're injective, and because of the injective we can compute the eliminator. So we tell you how to construct the type, and we automate how to deconstruct the type, sort of thing. And these are data types, but you can have co-data types, and they're not really very weird things at all. For example, this appears when you describe something not in terms of its constructors but in terms of its eliminators. So, for example, one example they like to give is like with infinite streams, where you can always read the next thing and there's still an infinite stream. But that's not an interesting example. They only give this example because it's a way of encoding infinite data in a total language. But there's a much more prosaic example, which is just record types in general. Record types in general are described by their projections. So when you define a data, actually it's a co-data type, the record, it's described by its projection. So you're telling people how to take it apart, and then the system generates constructors for the data type, for example, automatically. So this is the difference between co-data and between data and co-data. And a program, what is a program then? Well, what's a terminate? Well, again, like if you the distinction between program and co-program can only matter if you refer to total systems, or systems that terminate. So a program is something that consumes a finite amount of information and knowingly produces a finite amount of information, a result. So and it terminates. So you consume right. So you can consume more information, and it might take longer to produce the result, and so on. But basically, finite input and finite output, sort of thing.
Yeah, you will always get like you always get the response
Yes,
back
yes,
of
yes,
like
yes.
finite size in a finite amount of time, basically.
Right. But who produces the input for your program? Well, actually, a co-program. So if you think about this, not necessarily in terms of right, there's this duality between consumers and producers. So essentially, you can have a producer of data that has to be connected to the consumer of data, and they both have to satisfy this finite computation per finite data sort of restriction. So we're not dealing with like infinite programs and stuff like that, right? So whether something is a program or a co-program is just a realization of this duality between producers and consumers. Now, there's a precise way of explaining this using category theory, which I'm not able to do. All I know is that by talking to people who actually do know category theory, they did explain to me that Q programs are actually co-programs, so I believe them.
Yeah. I'll take their word for it.
Yes, but this reversal between bottom and top, essentially, that we see with traditional domain theory, which is applied only to programs, comes through this duality. Essentially, when we move from programs to co-programs, they also have this inversion. So yeah, this is somehow this is my level of understanding. I don't know exactly. So I hope I didn't say something completely wrong. But they are yeah.
We can edit it out otherwise. But just so to see if I understand. Like if I give an example, then if data is sort of a data constructor for a list, for example, then the functions like head and tail, for example, would that be like co-data in that case, or?
That's an interesting point. Let me think. Right. Well, because So yes, because it's the elimination form of a function. Yeah, sure. Yeah.
Because if I construct a list, for example, that's No.
Yes, functions are co-data for sure, because functions are defined in terms of their elimination forms. Yeah, that's absolutely right.
Yeah, I've been reading the little typer recently, so that was on my mind. But I think people should really check out Q, because it's very, very interesting. It's sort of like a mind-bending thing to take a look at. And and
it's a very simple language as well. I mean, that's again one of the main it's designed for engineers and programmers who maybe they even use dynamically typed languages or something like that. So it's designed for people who don't necessarily have any sort of advanced understanding of type systems, which is why it has such a simple model. Which is why I try to tell people, types in Q are like sets and stuff, because people understand set-theoretic operations such as like union, intersection, but also like a subset and stuff like that. They understand it. Well, at least intuitively. I mean, nobody does ZFC in their mind, I guess, but they do understand these things. So we say that types are like sets in Q. I mean, there's not. I mean, is it? That's the notational semantics. Let me just say that the notational semantics of Q is very non-trivial.
Because I was going to ask, like, how does it actually find refutations, for example, or detect not refutations, but how does it detect inconsistencies? Like, is that complex, or?
I have two answers, I think.
Okay.
Okay, one answer would be, so first of all, I actually said that it's actually a logic language. like in the tradition of Prolog and stuff. How do those languages work? Or what does that mean even? Well, it means, in Prolog also, you write axioms, and what the system does, this is the purpose of Prolog, which is different than Q, but this is the purpose of Prolog. Prolog will try to construct a model that makes the axioms, the horn clauses that you wrote through. This is what Prolog attempts to do. Right. Now, if there were an inconsistency, it means that the model would be empty. So this is one way you could do it, in the sense that, okay, if we have this, if we can compute these models somehow, and if we arrive at the empty model, it means like there's an inconsistency. Okay. But still,
you get false or no or whatever, depending on which dialect you're using.
So okay, but how do we do that specifically? Okay, well, in Prolog, I mean, one possible answer is to just look at how the unification algorithms work in Prolog, but I don't like this explanation at all, because the one particular unification algorithm is like a very arbitrary piece of technology, and it's like I'm looking for deeper reasons here. So, but one observation would be in Prolog, it's a bunch of equations, and running the program means solving a bunch of equations. In Q, it's a bunch of inequations, and solving a problem, running a program, doesn't necessarily mean creating a model, because that would be very difficult. It's with inequalities instead of inequalities. Doesn't necessarily mean, because we only care about creating a plausible description of a model. I mean, this is a subtle difference. And we're interested in not creating the empty set. And what does creating the empty set mean? I can explain it in a very geometrical or topological sort of sense. It means that, okay, let's step back one more step. What does it mean to have set-theoretic types? Okay. Or why are types not sets in the first place?
Yeah, that's a good question.
Okay, types are not sets.
Many people are wondering.
Types are not sets because for at least two different reasons. One of them is especially if you like a church-style type theory. Types are not sets because we don't say anything about sets. But there's not what we mean. People mean like, oh, but can we construct a set-theoretic model of a type theory? Or rather like a typed language. And the answer in the presence of general recursion is no, we can't, because a function from natural to natural, for example, is not the same. We cannot interpret a language like a process, like an algorithm from nat to nat. We cannot interpret it as a function from nat to nat because essentially the function space is too small. Essentially, non-termination requires us to enrich the domain, so we cannot just appeal to function. We have to. This was what prompted the creation of domain theory. So we have to create this denotational domain, which is much more richer than just functions. It's with complete partial orders and other more complicated things, which are simply not sets. So that's one answer. Another answer is so there's that. So okay, they're not sets. Now that's not to say that they cannot be sets in a total type theory. Not even in a total type theory, not all types can be sets, but certainly some types can be. Certainly a minority of types can be sets, and that's good. That's good, or can be interpreted as sets. Okay, another reason why types are not sets is because Reynolds wrote a paper called "Polymorphism is not set-theoretic." So we not even in the presence of totality, I think. Yeah, we have functions. not only from int to int or whatever, we also have polymorphic functions. Well, it turns out that a polymorphic function, as defined in System F and so on, does not admit a set-theoretic model. So, okay, this is sort of like technical thing. So, but the point remains that it's simply not possible to create in general set-theoretic models, or if we do, they're subject to all kinds of limitations around termination and stuff like that. And there's also like a approach. How do you define things? Because in set theory, you start with the empty set and just construct other sets from the empty set, which is not really the case of constructive type theory at all. It's very different thing that you're doing with type theory. And there actually is a distinction between terms and types, even independent types. Right. So okay. So what do we mean by set theoretic types? Well, I think the type theory people do think in terms of they want to construct set theoretic models of their type theory. That's not the sense that we're talking here. The sense that we're talking here is that we have a type. Sorry, we have a set that denotes that's large enough to encompass all types in our programming language, and we can construct this set. And then we interpret types in our language as subsets of that one. So it's not so much set theoretic types; it's like subset semantics, or I think that would be a better way of thinking.
So that's like lattice, right?
Yes, they have to form a lattice. They have to form more than a lattice. Depends if you are in a closed world system, and they have to form a Boolean algebra. In the case of Q, they form this thing which is almost a Boolean algebra, but not quite, called the Heiting algebra. But anyway, so we interpret types, programming language types, as subsets, and we interpret them semantically. This is a difference. This is this association between this semantic notion of typing. But what do we mean by semantic? Well, we mean, because we have constructed this semantic model, that's what we're doing with denotational semantic. We tie syntax to semantics. Whatever happens in the denotational domain, in this case, this particular one that we're talking about here, well, it's the semantic properties happen there. Like different types have different relations, in particular because it is a set. We're dealing with sets in the model, so they have like relations between them, like subset relations, or things like that. And when we talk about semantic typing, what we mean is that the rules for typing are actually properties of the model. So we have to look in the model to see what properties they have to determine questions like, is this a type or subtype of the other type, instead of doing syntactic considerations, which is what we normally use. We normally use like a syntactic rules for dealing with type assignment and type compatibility and stuff like that. So okay, so we have this set theoretical model, which is basically we have a set big enough to contain all our types, and all our particular types are subset of those, and they form relations. And in Q they form exactly the relations you want, in the sense that the type denoted by, say, nat is a subset of the type denoted by int, for example. But all of them are subsets of the universal domain, for example. Interesting things happen when you add functions. Very interesting things happen. It's again for the same sort of, well, first of all, Q, as I said, it's not a language where you do abstraction and composition using functions. You do it using this unification procedure, but it still has the same sort of problems that appear when you try to interpret functions as sets and so on. But to give a more prosaic example of where things can go wrong, is that types have this dual interpretation of requirements and descriptions, let's call them, which kind of it's this, if you view them as data or code data, and for data you can view them as both. That's fine, at least if it's finite. But when we add functions, we're starting to see problems of variance and co and contravariance, and this depends on how we interpret functions. Because so in terms of Q, if you have like the top type which denotes all the value, and we say x is top, and then we say x is int, it becomes smaller, and then we say x is greater than 5, it becomes smaller again, and then if it says x 1, it's 6, it becomes one element set, so a singleton set, so it always becomes smaller and smaller and smaller. Oh yeah, that's okay, but then what is the universal function type? You might be thinking, oh, it's like it's a function from top to top, but is it? Because there are different choices you can make. For example, if you take a function from bool to bool, well, there are 4 functions, four possible inhabitants of these types. This type. Well, you think so, because then I say, okay, I have a function from bool to bool, and that it only has possible 4 inhabitants, but I claim that that function intersected with another function from int to int, it's a subset of the original function, because it's a subtype of the original function, because it's in any context where you would need a function from bool to bool. If you instead provide the function from bool to bool and a function from int to int, it's just as good as a function for bool to bool. So this function, this new type, is actually a subtype of the original one, and actually it appears to have more elements. So that's an interesting observation. So okay, so there's a solution to this. Well, first of all, it's not a problem. Like you would think you would think this is a problem. It's not a problem if you are willing to not interpret any value as a set. If you're willing to do this, if it's like a particular encoding and there's like this when you have contravariance, which is exactly when you have function types, because because types appear in the negative position. If you're willing to have an arbitrary set-theoretic interpretation which doesn't the direction of subtypes, the direction of set inclusion in the model is reversed from what you want in the types. If you're happy with that, that's fine. But we're not happy with that, because we try to explain to people that these things are types, and we want to have them interpreted as types. But this means that we have to make a very specific distinction between producers and consumers, which actually sadly doesn't exist in Q today, and it is a problem. That we have to be precise about this. We have to be precise about positive versus negative types, and we currently in Q there's no way to do this, and which is why in Q currently it does not have user accessible function types, because we don't want them to be able to detect this problem yet, at least. Although it does have functions, but it's awkward that you cannot refer to their type correctly currently.
Okay, so that's how that. Because I was wondering a bit about the functions as well, like because it seems like there are functions, but okay, they are the built-in functions.
Well, okay, and right. So as I said, so there are different ways you can try to fix the problem.
Sorry, just to interject.
Yeah.
But I think I have to stop the recording soon.
Yes, of course.
But I just wanted to ask really quick, like you were also like working on a programming language.
I am.
Of your own.
Yeah, I am.
Can you give us like the elevator pitch?
Yes.
What's the big idea?
Big idea is that programming should be simpler. And
I agree. Yes.
And also simpler, flexible, safer, cheaper, and also it should be you should be able to reason about things like the representation, memory layout, and also like performance. So it should be uncompromising on any of those things. So it should be, which is usually the low-level languages try to sell you like that. Oh yeah, you can reason about memory, great, but you don't have like higher abstraction ceiling or something. No, I think you should absolutely have both. So the elevator pitch is that it's a language that first of all allows you to reason about representation and about the computational efficiency, in the sense that it directly makes use of linear logic.
Okay.
In a strong sense, not like Rust, because Rust is just like a regular language, like take lambda calculus, and you add, like, linear logic is a very rich thing. It doesn't have only like linear types, which in Rust are not even linear. They're affine types in Rust. There's more to linear logic than just that. Linear logic is basically it is a logic of resources, but it's also a logic of processes. And guess what? Everything can be interpreted as a process in what we're doing with computer science. So that's perfect. We have high-level processes, of course, but even in the microscopic sense of like functions can be processes.
Okay,
as well.
Function can be a process.
Right. So
like
okay. So first, it's supposed to be simple. So it is a way to. Okay, why is computation hard in Rust? Well, okay, borrow checker and so on, but no, it's because computation and data are separate, and the technology that brings them together is very primitive, and it's very hard to, like, when you create a data type, you have to really commit to it, and you can only take it apart in a specific way, and then if you take it apart, you can't put it back together. So what we really need to be doing is having a more fluid way of moving between computation and data, and not just move data to the computation, but move computation to the data as well. So if you have I mean, this is kind of what map does in functional, at least semantically, what we like map in functional programming is that we have a list or whatever, and when we map over it, well, okay, we construct a new list, but it's as if, especially in a linear setting, when we consume the original one, it's as if we move the computation inside the list. That's exactly what we want to be able to do, except in a far more general setting, and in a way that it solves all the problems with Rust in terms of the lack of flexibility that comes from the borrow checker, because we can reason about codes instead of types. Programming with codes is a first-class citizen. And what do I mean by that is that what are codes? Well, codes. If you're dynamically typed programmer, you've only seen codes. So code, essentially, when you're writing a program, you have to encode something about the real world or about the problem you're trying to say, and it's encoded in some value which may or may not have some properties, and you're doing operations as in a sense of algorithms on that value, and the hope is that the operations that you're doing somehow reflect meaningfully what you're trying to achieve, and this and it's a hope. This is hope-oriented programming. The dynamically typed programming is basically based on hope. Hopefully, it works well.
So yeah, basically you're saying that, like, okay, so I sort of have to track mentally that, like, this string over here is actually like an email address. That's how you do it in practice. But on a conceptual level, when we're programming with types, we're programming directly with meanings, in the sense that we ascribe meaning to types, but also the language, the compiler,
the system that compiles the code has the same understanding of those types as we do. So we're in full agreement with the language of what is the meaning of what we're doing here. And the language doesn't let us do meaningless things. Now, when we program with codes, we can't do anything we want because there are no restrictions, so we can lose track of this meaning. Now, one thing, so I, a big proponent as someone who believes in types, of course I'm a big proponent in programming directly with types, that is meanings and not codes. However, there's always going to be a limit on your type system, and you're always going to have, at some point, have to program with codes. And that's fine. All I'm saying is that the programming language has to support programming with codes just as well as with meanings, and it's not that difficult to do. Because what that means, and I'll give an example in Rust. So in Rust, when you have cyclic data structures and you cannot represent them with references, the solution, everyone says, please do this, is to use, for example, integer indices in some array or something, and you represent.
So like an arena.
Yeah. But the problem, and this absolutely works, and then those indices become like a substitute, like it becomes a piece of information that you can use to get to the value that you want. However, we lost something very important in the process, because references give you all kinds of properties, such as, well, one of them is like you cannot misuse references, like use after free and all that stuff. Whereas an integer index in an array, of course you can do that. Now it's not a memory issue because of course Rust is memory safe, but it is a logic issue. So we lost whatever benefit the type system claimed to have in terms of being in union with meaning, as in terms of meanings with us. We lost that information because we had to encode it in some other way than directly with types. And
you're saying, like, for instance, you could actually by mistake mix up one of those indices with an integer that you were supposed to store in the arena or whatever,
or use one index in some arena in the wrong arena, or
that's true as well,
or something like that. And this problem is solvable. It's even solvable in Rust if they add a form of genericity for type generation, but it doesn't matter the particular solution. But the idea is that when I want to say that I want to give meaning to programming with codes directly, I mean that yes, we'll do it just like in Rust with indices and stuff like that. But we can express additionally the properties that those indices have to come from the right array and have to be used in the right order, so that we don't do use after free and all that stuff. This is extra information that we can reason about if we have a curry level type system and we have these intersection types, and also can do it with dependent types and stuff like that. So in the language that I'm working on is very well suited to solve all these problems where you have to change the encoding of something and you lose direct typing of it, essentially, because you're essentially constructing a model of the thing, not just the thing itself. You're constructing your own universe, which has to have specific rules, but you don't want to lose. You still want the language that embeds your model to help you with types and such. And I claim that so in the language that I'm working on, again, using curry level type technology, you can add types to these codes as precise as you want or as loose as you want and get the same benefits while still getting all the same benefits that you get from Rust, for example, except it's even safer now. And it's also much easier because you can do cycles and all that stuff easy.
So you can basically say that, okay, so like not only is this an integer, it's actually pointing to an address someplace in this memory soup, or like pointer soup, or memory arena, or whatever you want to call it. And also that maybe like it has a range of this start and end, etc. that maps to the...
Yes, and it's done. Again, linear logic helps here from a theoretical point of view, because in linear logic, so in a normal programming language, if I give you a record type, you can always project out of it. So you can forget part of it basically, and that's still possible with linear logic. But it's also possible to encode the record type in a different way, in such a way that it's not possible to lose track of the relation between its projections, and that means that you can put you can attach to a record type another type, which is a proof of some specific relations that those values have to have, and you cannot confuse your proof with different record because you cannot take it out of the record. Linear logic doesn't let you do that. You can do it, but you destroy the record. So on the other hand, there is enough technology that allows you to then use the fields in the record, so its projections, without having to take it apart. Because that's the if we have to take it apart, then we lose track of this thing. Well, then we don't want that. So we want to be able, but then again, if we pass, so if I have a record with two fields like a string and an int, and I want to operate on an int, I want to write a function that takes an int. I don't want to write a function that takes the whole record. I could do that. I don't want that. But so I can do that while still not losing track of the original record, and it's still mutable and all that, by the way, and it's still type safe with dependent types and everything. You can arrange for this sort of encoding basically. So you can get let's say it you can reason about the properties of more than one values. I mean, you can in any language that has advanced enough types, you can reason about the properties of a single value. You can invent a new type that represents some property. But if you want to capture the property of a relation between two values, you have to bundle them in like a tuple or whatever. But then you can't take them apart, or you can take them apart, but then you lose all this information that you get.
Yeah, you don't have the provenance
exactly. It's exactly right. It's about capturing the provenance information, right, of values, while still allowing them to be related, and you get the flexibility that you can pretend that you can take them apart, but you don't have to. Yeah, basically the language keeps track of these linear logic unpackings and packings for you.
Yeah, that's very interesting. Unfortunately, I don't think we have time to dive into the whole linear logic thing. But one thing, just a short question, if I may, is because we mentioned already, like the fact that new types, they're usually substitute for I don't know, proper proofs. Yeah. For example, if we return to the email address example, like a strong enough type system would be able to carry around the proof that this was a valid email address, or was validated to be a valid email address. But given in the absence of that, we usually use this new type pattern where we have the smart constructor, etc. But another, so that's one use case. But another use case is to track provenance of things. For example, so a common use case, for example, is kind of like you mentioned with the arenas, that you have let's say you have a UUID, for example, that comes from a database that's used as a primary key in one table. You don't want to mix that up with another GUID or UUID that comes from another table and is used as another primary key. And you're saying that, or could linear logic be used to sort of track these things,
with dependent types? Yes, because those two things are different things created at runtime, and you need the type or some compile time distinction between those two things, as to not confuse them. And of course, dependent types can do that, but basically, it just means that you need to be able to create a new type, essentially. Now, there are other languages. In OCaml, you can do this, by the way, with functors, generative functors. Like in OCaml, that's the point of generative functors, to generate a thing that is distinct. Like there's a distinction between generative and applicative functors. You can make the applications different, and you can keep this distinction at the type level, basically, such that it's impossible to confuse those two things and misuse them. Now, of course, it's very inconvenient. So I want to be able to do this in a far more ergonomic and first-class fashion. So this is one of my primary considerations. Like how can I make this really ergonomic and really simple? And yeah, I 100%. This is an important feature, and you can do it with depend. And linear logic certainly it has a part in it, because linear logic and session types are very related to one another. And this is what you just explained is basically just another example of a session type, because you get these tokens from somewhere, and you have to respect this particular protocol in order to use them, while keeping track of provenance information. And speaking of provenance information, by the way, this is Rust. I mean, every language, of course, because it has the linear types, it still has this friction with provenance. And I said, if you have a struct, you don't want to take it apart, and it tries to solve this problem with borrowing. Borrowing it basically is just a compile time mechanism of keeping track of provenance, so that this works. But the problem with borrowing is that it only works if your program is arranged in such a way that it respects a stack discipline. It doesn't work in the general case when you have like a more symmetrical view of processes and consumers. Rather, it kind of only works with like consumers which can mutate data and stuff like that, because it has to have this stack discipline where you thread things to one function to another function. And if you can do that, it's great, but it's a very severe limitation.
Because it only basically works with like allocation and for anything that follows the pattern of allocation and the allocation. Exactly.
But I want, essentially what I want are first class lifetimes, where you can put them in variables and stuff, and then you use them like in a protocol, but the usage is statically checked in a very strong sense to not be able to do exactly the things that you were talking before. And so this is one of the things that I doing in this language. And I must say that it's I don't think I'm inventing anything at all. It's in some way very conservative with new inventions. It's just application of known theory as much as possible. I mean, of course, combining all these features in practice, and plus, of course, I have like algebraic effects and other things. I just clearly work.
Of course,
it's clearly work to be done there, and to combine these things properly. However, it is a very explicit goal of this project to be as conservative with features as possible, because we don't want to tread like a unknown space or something. We were looking for I am looking for known theory. And by the way, I said it's, of course, clearly I'm a big fan of like query level types, but I want my language to be able to have a very good control over memory layout and so on, not just because of performance, but also, more importantly than performance, as far as I'm concerned, but for expressivity. For example, when I receive a network packet, it has a specific memory layout. As far as I know, only Erlang, maybe Elixir, I'm not sure, but Erlang is the only language which can even express this idea. You can match on a bit string, but it's not a type. It's just the way you match on it. But the point is that I want to be able to take a network package, which is an allocated piece of memory, and interpret it using whatever type I want, but without doing any sort of parsing or copying or anything like that. So
I have to chunk it up, basically.
Yeah, exactly. And I have to. So there's this idea of representation type, which is actually a church level type theory, which underlies the whole language, because it also has to be compiled efficiently, and actually it's very difficult to compile a curry level type efficiently, but I want to be very high performance language here. So actually a church type system, this is one of those advantages, they help. So the underlying, there's a core language and a core type theory that's church typed, and it should be high performance and whatever with linear logic and stuff like that. And then you build on top of that another layer of a type system of interpretation types that's a curry type system, and it's completely user controlled, and it's completely in user space. It's the compiler doesn't have to know anything about anything. You can implement your own type system, and the existing type system is just a library. And this is important for even including reasons such as the language, the ease of implementation of the language. If someone who wants to implement your language has to also implement a very particular type system, which by the way you might have to change because it's an early language and you get something wrong or whatever, that's a disaster. Whereas it's relatively simple to implement like a very simple language. It's just like lambda calculus and stuff like that with a church type system that just gives you like performance and everything. And there's nothing controversial or new about this. But if the type system is completely in user space, then if you do a new implementation, you can just port the type system because it's just user space code. So this is another advantage of curry level types. So it has to be user space.
You could also implement the type checker in the language itself, right?
Yes, you could, and ultimately that's what you have to do. But it's very first class. So it's like it has to be basically a library. I think it has to be like it doesn't have to be privileged code in any way. It doesn't have to have and this language is to be able to do this. It means that you have to be able to reason about the syntax, because that's how if you claim it has a type, you have to check how you have to check. You have to check the type constructions rule on the syntax. So this library has to have access to syntax, which kind of sounds like macros, but no, there are no macros. Okay, there are macros in that sense because they input is syntax. However, they cannot affect the evaluation of the language in any way, and that's a critical property, because one of the problems with macros, and one of the reasons people really don't like macros, I know Lisp people of course love them, but in the industry people don't like macros because you cannot understand the semantics of the code locally, because it depends on some other thing somewhere else. Whereas no, the language has to be perfectly understandable just from reading code, and it has to be understandable without context. So it has to be like it's like a purely functional in that sense. You have to be able to understand fragments of code just fine. Like the denotational semantics is like perfectly compositional. All these macros they can do is add more types to it, but more types, as we just learned, types do not have any impact in evaluation, so they do not change the semantics. Type just gives you additional semantics, and they can stop they can prevent code from compiling, so that's fine. You have code that would normally compile, you invent a new type system that's more sophisticated, and for some reason it decides to prevent this particular code. For example, maybe you want to restrict yourself to the subset of the language that's total and always terminating. That's fine choice to make, but it doesn't. All the terminating programs, of course, the type system would reject some programs, and that's fine, but it will never influence the semantic of the code in any way. I think it's a critical property.
Yeah, that sounds very interesting and quite mind-bending as well, to be honest.
Well, I think first, when you're designing a new programming language, you have to decide where you put your, let's call it, strangeness budgets. Like every language has to be different or have some interesting idea or something. Otherwise, it's pointless. And it's very important to have a grasp of exactly where are you innovating, or where at least you propose that people do things differently, and where do you propose that people keep things the same. if you want to have any success, and you have to be very clear about the delineation about these things, and I would say be as conservative as you can with things, but at the same time you have to be very bold with your features and commit to them and explain to people why you have them. So I would say it's not the reason I'm doing another programming language is not like okay, first of all, of course there's the frustration because I understand that the systems that we use today are limited in some particular way, and I know I can do better. But I think it's more general than that. It's not just the programming language. It's like this whole software ecosystem, including things like how do we edit code, how do we represent code, like in text file or whatever. All the system has to work together holistically in a way. So when you propose, essentially you're inventing a new ecosystem more so than just a particular language. Of course, it has to have a niche, and I mean, you have to target a particular problem, a particular group of people who have a particular problem, and solve that problem particularly well. But I also think you have to think of larger concerns. Because I have so much experience with like low-level systems engineering, it's a good starting place for me. One great advantage this space has, like also like if you think like aerospace or embedded stuff, is that they don't have any dependencies or libraries. They don't need any libraries and stuff like that, which is different from the majority of other programming that we do these days, where basically in practice the programmer just glues things together and they have to have libraries, and not having libraries is a huge bootstrapping problem for a language.
Yeah, the ecosystem is the most important part.
Yeah,
sometimes
the JavaScript things like the TypeScript and all those JavaScript things, at least they even if you make a new language, you can still leverage all the existing JavaScript infrastructure, so you have something to go there. If you do Rust, I mean, it's not ideal, but you can absolutely interact with C from Rust relatively easily, for example. But in general, this is a problem. My way of dealing with this problem is by decreeing it's not a problem, because with low-level stuff it doesn't matter. But but of course I hope that, you know, as the language evolves and progresses, and it will become more general, and then people will start writing libraries and stuff like that. Right.
Yeah. Well, I mean, I'm very excited to see where all of this is gonna go. So I don't know. But yeah, we're running out of time, unfortunately. But I guess I'll have to invite you back next time once the first alpha version of the language is out.
Exactly. Yes, I would like to be back and talk about this language. Basically, the status is that, I mean, I decided to do this a decade ago in some capacity. Of course, I haven't worked on it all the time. I mean, only as much time as I had available and stuff like that. But most of the work done so far was research and learning. I mean, when I decided to do this, I didn't know anything about programming language theory, basically. So there was a lot of learning, and more importantly, there was a lot of prototyping done in many other languages, in the sense that I know that I have this algorithm that I want to write, and I want to be able to express it nicely in my language. But I now I know that I can't express it in all these other languages. But a lot of prototyping work has been done, especially with memory allocators, including fake things. Like, of course, you don't write a memory allocator in Haskell, but you might as well write something that behaves like a memory allocator in Haskell, just to see how fluid and easy to do this sort of thing is, and stuff like that. And in low-level languages, including Rust, it's very difficult to do this sort of thing. So basically, I identified what are the pain points of existing systems, but also how does higher-level programming, including things like dependent types and stuff. I also like a lot of prototyping in Lean, for example. How can I express these things more easily? And then I can see, okay, I can express these things more easily using this particular variant of dependent types. okay, but then then I have to think of how I could add it to my language with the constraints that it has to be curly based, and maybe I don't want dependent types in the sense that if I could avoid them, it would be good. By the way, we haven't talked about this, but intersection types are great not only for the flexibility, but also a lot of the use cases where you would use dependent types for can be done using simple intersection types, because a lot of the things where you just you'd have a dependent pair, you can instead have an intersection, and it's both simpler to understand and less in engineering costs and stuff like that.
Yeah.
So
I mean, you can check out like TypeScript function overloading for a good example of this, like, you know, and because they also have like type level literals and stuff like that, you can get like, I don't know, maybe 80% of dependent typing is an exaggeration, and it depends on what you mean as well. But I mean, it is for some use cases, it's more than enough.
Yes, I agree, and it's also it's about making things as easy as possible for the end user while giving them as much guarantee as possible. Basically, best bang for the buck. Dependent types will never gonna be like a mainstream thing. I don't believe they're gonna be. I think they should be available for those use cases where you need like maximum reliability and so on. And yes, people should be using them back then for that. But I really think you should be able to I think we can improve the reliability of programs even without dependent types, and I think we can live in a world that naturally translates between simple and dependent types without having to pay any upfront costs, basically. Or at least that's my goal, and that's what I'm trying to do, and and I'm trying to do it in a very different way than Idris, for example.
It will be very interesting to see where that goes. Yeah. But yes, thank you so much for coming on the podcast, Aram. I feel like I learned a lot.
Thank you for having me.
Gonna blow up.
Yes, thanks for having me. It's been great. It's been great. Yeah.
Yeah, and like I'd love to have you back sometime, and like maybe around the release of the first version of your language.
Yes.
Very good.
Yes.
But until then, have a nice day.
Thank you. You too.